Always this electronic circuit or logic gates which works on one or more input, or we say input signal. If you have one input signal, there are two possible combinations, and these combinations are we are representing in the form of a table. It is called as truth table. X and Y, these are the input signal. Output is X plus Y or F. Here plus stands for OR gate. Dear students, welcome to our computer science classes. I am Ravi Kumar KR, lecturer in computer science, Vidhyaashram PU College, Temple of Excellence, Mysuru. Students, in this session, we are going to discuss about logic gates. It is a new chapter, that is chapter 3, logic gates. In this chapter, we are going to cover or we are going to learn the basic definition of logic gates, basic logic gates, derived logic gates, and design logic circuit for the given equation, and NOR to NOT logic, and NAND to NAND logic. See, these are a few concepts we are going to learn in this chapter, logic gates. First of all, let us see the definition of logic gates. What is a logic gate? A gate is simply an electronic circuit which operates on one or more signals and always produce one output signal. And these logic circuits used by the processor of computer system. Here, what are logic gates? It is an electronic circuit. The meaning of the word electronic circuit is nothing but the electrical circuit. Now, all of us know that what is an IC? That is integrated circuit. See, integrated circuit is made up of, or inside that we can find thousands of electronic circuit. So your IC, integrated circuit, it contains so many or number of electronic circuit. So actually this electronic circuit or another name is digital circuit. Now this we know the definition of computers. Computer is, we say it is an electronic device. What is the meaning of the word electronic device? Because these electronic devices which works on the principle of logic circuit. That is why we say it is electronic circuit which operates on one or more signals. So always this electronic circuit or logic gates which works on one or more input, or we say input signal, and always gives or produce only one output signal. Here, what is the meaning of this? Here if I say the signal is in the form of 0 or 1. Here there are these signal, there are two states. There are two states of the signal. One is 0 state or one is 1 state. This 0 state is referred as off state and it is on state. And another way, thus we can also say this is true and this is false. So what are the meaning of the signals here now? These electronic circuits or digital circuit which accepts two or more input signals. So here all signals are in the form of either 0 or 1, and there are only two states, either 0 or 1. So these type of circuits are present inside ICs or microprocessor. That is how the computer works, or that is computer processes the data and uses the result by using these electronic circuits through the electronic signals or digital signals. So that is the definition of gate. So logic gate or a gate, electronic circuit which takes or accepts one or more input signals and always produce one output signal. So this is the definition of logic gate. Now let us see the different types of logic gates. Generally there are two types of logic gates. One is basic gates and second one is derived gates. So what are basic gates? The basic gates are NOT gate. It is another name of this gate is inverter gate, OR gate and AND gate. These are called as the basic gates. And another category is derived gates. What are derived gates? Derived gates are NOR gate, NAND gate, XOR gate. X stands for exclusive OR gate and XNOR gate, exclusive NOR gate. So what are the derived gates? Derived gates are those gates which are derived from the basic gates, or in other words, we can construct another circuit or another digital circuit with the help of these basic gates. That is the definition of derived gates. Now let us learn these gates one by one in detail. The first circuit or gate is inverter gate or NOT gate. NOT gate, another name of NOT gate is inverter gate. What is the definition of it? An inverter gate is a gate with only one input signal and only one output signal. So this inverter gate, it takes only one input signal and gives us or produce only one output signal, and the output state is always the opposite of the input state. So output state is always the opposite of input state. What is the meaning of that? In previous slide I told you about the status. There are two status, one is 0 and 1. So here the opposite of 0 is 1 and opposite of 1 is 0. So here the result is that if the input signal is 0, output signal is 1, or if the input signal is 1 and the output signal will be 0. This is the meaning of the output will be always the opposite of input signal. Now let us see the logic symbol or digital circuit or logic circuit of NOT gate. You can see a diagram here. This is the diagram or logic circuit, and here X is the input because it takes only one input. So this is X is the one input and always X0 is the output. So here X0 is the output, one input signal and one output signal. And this NOT gate we are representing with a bar. This is a bar, this is bar, or we are using tilde. One more symbol is using single quotation mark. So here X is the input here and output we represent with X0, or this is tilde X or X apostrophe or single quotation mark. So this is how we represent the NOT gate. So X is the input here, output is X0. Now if there is only one input signal, here we can find there are two possible combinations. For example, if you look at the diagram here, this input can be either 0 or 1. Suppose if it is 0, output is always the opposite of input, that is output is 1. So this is one combination. So what is another combination? Here another combination can be input is 1 and output will be 0. So in this example there are two combinations. If you have one input signal, there are two possible combinations, and these combinations are we are representing in the form of a table. It is called as truth table. And what is a truth table? The possible values of input signals and along with the output we are putting in the form of a table. This is called as truth table. Now we can observe here, this is the X is the input here, and here there are two possible combinations, 0 and 1. There are 0 and 1, output would be 1 or 0. So this is the truth table for NOT gate or inverter gate. Now let us move on to next slide. Now this is another type of basic gate, that is OR gate. What is the definition of OR gate? The OR gate has two or more input signals but only one output signal. What is the definition of this? If any of the input signal is 1 or high, the output will be always high. High stands for 1 is the output states or input state. So this is the logic symbol or logic circuit for two input OR gate. Here this A is one input, B is another input, F is the output here, and here there are this is 3 input OR gate, this is 4 input OR gate, and this OR gate we represent with the symbol plus. We represent OR gate with plus symbol. So this is the logic circuit and this is a definition of this. If any of the input signal is 1 or high, output is high. Now let us see the truth table of this. Look at the truth table here. There are two x and y, there are two inputs. So we can find out number of combinations with the general formula 2 to the power of n. Here n stands for number of input. N stands for number of inputs. If there are two inputs, so there are possible combinations 2 to the power of n, that is 2 squared, that is equals 4. So in this example, we can have 4 different combinations. Look at the example here, 4 different combinations. So there are two in this, look at the truth table now. X and y, these are the input signal. Output is x plus y or f. Here plus stands for OR gate, or it indicates OR gate. Now here, what are the 4 possible combinations for this? Now here, if you look at the previous slide, now let us look at this example now. Here there are 4 combinations. What are the different combinations are possible here? Either in this example, this can be 0 or this can be 1. This is one output, one input combination, or this can be 0, this one can also be 0. This is second combination. And one more combination, this one will be in 1, this is 0. This is another combination. And fourth combination would be 1, 1. So in this example, there are two variables, 2 to the power of 2 equal to 4. There are 4 different combinations. So one combination is 0, 1. If this is 0, 1, what is the output? If it is 0, 0, what would be the output? So all these we are recording in the form of table, that is truth table. Now we can observe the truth table here. So these are the 4 different combinations and 0, 0, 0. How do we write this output here? As per the definition of OR gate, any of the input is high. In this example, no inputs are high, means 1. No input is 1, output will be 0. Now look at second combination here, 0 and 1. In 0 and 1, this input is high, output would be high. So look at this 1, 0, 1, 1, 1, 1. If you look at the input combinations, wherever, if at all, if there is at least one input signal is high, output would be high. That is the definition of OR gate. Similarly, now you can see the truth table for 3 input OR gate. 3 input OR gate, X, Y, Z are the 3 input signals, and here f is a function equals x plus y plus z. Here plus stands for OR gate. Now let us see the different combinations. Here in this example, there are 3 variables, n equals to 3. That is 2 to the power of 3, that is equals 8. So it is possible to have 8 different combinations of 3 input signals. Which are those 8 combinations? See, these are 1, 2, 3, 4, 5, 6, 7, 8. And here, how do we write truth table for our convenience? Generally, we write like this. Here, there are 8 combinations. So, half of 8 is 4. Half of 8 is, that is 4. So, we start with first 4 zeros and next 4 ones. So, there are 8 combinations. This is one input signal. For the second signal, here there are 4 zeros and half of it is 2. So we write 2 zeros, 2 ones. 2 zeros and 2 ones. Similarly, this half of 2 is 1. So we write 1, 0, 1, 0, 1, 0, 1 and 0, 1. So this is generally we follow to write the truth table. If there are 3 variables, there are 8 possible combinations. These are the combinations. And what would be the output of this? The output signal, if you look at that here, the definition says that if any one of the input is high, output is high. If you look at this combination, here none of the input is high, output will be always low or 0. Similarly, if you look at this combination, here is 1, output is 1. So in all the combinations, wherever there is a 1, at least one input state, output will be 1. So this is the truth table for OR gate. Now let us move on to one more gate, that is AND gate. What is AND gate? Again, it is a digital circuit or logic circuit. It takes two or more input signals and always produce one output signal. That is the common definition. And here, what would be the output of this? Here, when all the inputs are high, then output is high, otherwise output is low. That is the basic definition of AND gate. Now you can see that here the logic symbol of this AND gate, this is two input AND gate, A and B, F is the result, and here AND gate we represent with dot, that is single dot. So output will be here either F, nothing but A and B. This is A and B. This is the output of AND gate. Similarly here, this is a logic circuit for 3 input AND gate. There are 3 inputs here. Output is F. We represent output with 3. A dot B dot C. This is the output of this 3 input AND gate. Similarly, this is 4 input AND gate. These are the symbols or logic circuit for AND gate. Now let us see again the truth table for AND gate. Here in this example, there are 2 input AND gate. So there are 2 input. As already we have seen how to write the combinations by using the formula 2 to the power of n. With the help of this, we can write these combinations. There are 2 variables or 2 input signal and output there are 4 different combinations. So what would be the output of this? As per the definition of AND gate, see the definition here. When all the inputs are high, then the output is high, otherwise low. Means when all the inputs are high. Now in the truth table, you can see that here none of the inputs are high, output would be 0. Similarly here, only one input is high. So definition doesn't hold good, so it will be 0. Even in this case, and look at the last combination. Here 1, 1, 1. In this input combination, there are 2 ones or all the inputs are high, output would be 1 or high. This is a 2 input AND gate. We represent with X dot Y, that is dot represents AND gate. This is a truth table for 3 input AND gate. There are 3 input signals or variables X, Y, Z. Here again we know just now I have told you how to write truth table with 3 input signals, that is 8 combination. First 4 zeros, 4 ones. Next 2 zeros, 2 ones. And here 0, 1. That is how we write the input combinations for 3 input signals. Now output is, as per the definition, when all the input signals are high, output is high. If you look at the combination here, except last one, in all other 7 combinations, all inputs are not high, so output would be 0. Only for the last combination, in this example, all the inputs are high, output would be 1 or high. So this is truth table for AND gate, 3 input AND gate. Now let us move on to next slide, that is derived gates. What are derived gates? As I told you definition in the beginning itself, these are the gates derived from basic gates. Means we can construct different types of circuits or different types of logical circuits, digital circuit by using 3 basic gates. They are AND, OR and NOT. Now let us see about one of the derived gate, that is NOR gate. NOR gate is a derived gate. Now look at the definition. A NOR gate has 2 or more input signals and always gives 1 output signal. That is a common sentence. Next, what will be the definition of this? If all the inputs are 0, if all the inputs are 0, nothing but low, then the output signal is high. Definition of this, when all the inputs are 0, output signal is high. That is the definition. Now look at the circuit diagram of this. See, this logical symbol, how do we write the logical symbol for this? If you look at NOR gate, it is derived from basic gate. By looking at the gate here, you can make out this is derived from OR gate. So, what is NOR gate? NOR gate is OR gate followed by NOT gate. I repeat, this NOR gate is formed by OR gate followed by N. Here N stands for NOT gate. Now look at the logic symbol for, see, this is the logic symbol for your OR gate, and OR gate followed by NOT gate. Here you know that this OR gate can have more than 2 or 3 input signals, but this NOT gate, inverter gate, you will be having only one input signal. So output of this will be the input of this NOT gate. So by considering these two, we can write finally the logic symbol like this. See, this is the logic symbol for 2 input NOR gate. So what is a NOR gate? NOR gate is derived from the basic gates, that is OR gate followed by NOT gate. This is 2 input NOR gate, and this is 3 input NOR gate. This is 4 input NOR gate. Now here, if input here, this is X and this is Y, these are the 2 inputs, and here output would be here X and plus Y. This is OR gate followed by NOT gate. So this is how we represent NOR gate. So now let us see the truth table for this. Now again, there are 2 variables here, 2 variables, 4 combinations. There are 2 0, 2 1, 0 1, 0 1. And how do we write the output for this? See, this is F, and we say X plus Y, and over it, it is a NOT, that is a bar. That is how we represent NOR gate. Now look at the output of this. Here, as per the definition, when all the inputs are low, output is high. That is the definition of this. According to the definition, if you look at this combination, here all the inputs are low, output would be 1, or the result is high. In rest of the combinations, here not all the outputs are 0. So because of that, here it results with 0, 0, 0. So this is the truth table, or this would be the output for this NOR gate. This is truth table for 2 input NOR gate. Now let us see the truth table for 3 input NOR gate. Again, there are 3 input X, Y, Z, 3 different signals. Again, there are 3 variables or 3 signals, 2 to the power of 3, 8 combinations. Here 4 zeros, 4 ones, 2 zeros, 2 ones, and 0 1. So this is how we can write different 8 combinations. Now let us write the result or output for these combinations. See, as per the definition, when all the inputs are low, mean only in this truth table, only in first case where all the inputs are 0, nothing but low, definitely output would be 1. So in rest of the combinations, result would be 0 according to the definition of NOR gate. Now let us go to next slide. This is NAND gate. Again, it is a derived gate, derived from basic gates. Now let us say this NAND gate. Again, here by looking at the NAND gate, you can make out this is AND gate followed by NOT gate. That is NAND gate. AND gate followed by NOT gate, and definition, it has again 2 or more input signal, and always it gives us produce 1 output signal, and if all the inputs are high, output is low. That is the definition of NAND gate. If all the inputs are high, output is low. Now look at the symbol for this. As it is derived from AND gate, this is a diagram of AND gate followed by NOT gate. Again, the output of this AND gate will be the input of this NOT gate. So finally we say if this is A, B here, and output will be Z, and we represent NAND gate with A is 1 and dot B. This is AND gate followed by NOT gate. See, this is how we represent the output or the result Z. We are replacing this with this symbol. This is how we represent AND gate, and this is a small circle, we say bubble. So AND gate with the bubble is your NAND gate. Now let us see the truth table for this. Truth table, it is for 2 input NAND gate. Again 4 combinations, and as per the definition, according to the definition of NAND gate, when all the inputs are high, output is 0. In rest of the combinations, it has either 1 or 0 status, or to 0 or 1 signal. So because of that, output will be 1. Now let us look at truth table for 3 input NAND gate, 8 combinations, and here output here. What as per the definition, when all the inputs are high, output is low. So accordingly, only for this combination output will be 0. For rest of the combinations, output will be 1. So this is truth table for NAND gate. Now let us look into another derived gate, that is XOR gate or exclusive OR gate. What is the definition of it? It says it accepts 2 or more inputs and always gives 1 output or output signal. And the output is 0 if there are even number of 1s in the input. Now the output is 1 if there are odd number of 1s. So this is how we write the output for. By looking at definition, we have to write the output for this XOR gate. Again the logical symbol, you can see that exclusive OR gate. See, this is OR gate, and before we have a small arc. This represents your XOR gate, exclusive OR gate. Here this is 2 input, and this is 3 input, and this is 4 input combinations. And next, now look at the truth table for 3 input XOR gate. 3 input, 3 signals, 8 combinations. Now look at the definitions. Output is 0, even number of 1s. Wherever you find even number of 1s, here even number 1, output is 0. In this example, in this combination, output is 0, even number of 1s. Here there are 2 input signal, 2 is a even number, so output is 0. And here in this combination, there are 2 1s, there are 2 input signals with 1 or high, 2 is even number, so it is output is 0. Similarly, look at now, output is 1 if there are odd number of 1s. So odd number of 1s. If you look into this here, 1 in this example, odd number of 1s, 1 is odd number, output is 1. Similarly, the odd number of 1s, 1. And here odd number of 1s, here 1, and here again odd, there are 3 here. So 3 is odd number, so output would be 1. So this is how we write truth table for exclusive OR gate. Let us move on to next gate, that is XNOR gate, that is exclusive NOR gate. This is exclusive NOR gate, and what is the definition of exclusive NOR gate? XOR gate is a gate followed by NOT gate or inverter gate. Now you know what is XOR gate, isn't it? This is, we have learned in previous slide, that is exclusive NOR gate. This is NOR gate followed by NOT. So this is exclusive NOR gate, and it takes 2 or more inputs and always produce 1 output signal, and it produce high output when the input combination has even number of 1s. Even number of 1s, it gives output is 1, or when all the inputs are 0, output will be 1. Now look at the truth table for this. This is 2 input XNOR gate. Here 2 signals, 4 combinations. What is the output of this here? As per the definition, if there are even number of 1s, then output will be 1, and even when there are even number of zeros. In this example, this is even number of 0. There are 2 zeros, as 2 is even number, output will be high or 1. Similarly, in the last combination, there are 2 1s, as 2 is even number, output would be 1. So this is the truth table for 2 input exclusive NOR gate. Now let us see the truth table for 3 input XN OR gate. There are 8 combinations. Now, in this example, here when all the inputs are 0, output is 1. That is as per definition, this is 1. And if you look into that, in this example, there are even number of ones, output is 1. In this combination, there are 2 ones, so it is output is 1. Even in this case, 2 ones, output is 1. And in last one, this is 3. 3 is odd number, so output would be 0. So this is a truth table for exclusive NOR gate. Okay. Next concept is circuit diagrams. Means to design a circuit diagram for the given functions or for given functions ABC. So in this example, you can see there are 3 input signals, that is ABC, and output would be AB. Here we have to read it as A and B. This is dot, and this plus stands for your OR gate. And similarly, this is one more input, A dot C naught. Here A dot C naught, and here plus, again this is the plus, and here is B dot A naught dot C naught. See, this is how to read the given equation. Here A and B. See, A and B, this is one A and B, it is your AND gate. And this is A and C naught, this is one more gate. And here B, A, C, this is another gate here. So here this is one gate, one AND gate with 3 inputs, another AND gate with 2 inputs, another AND gate with 2 inputs, and at last we have to give as a one input signal by combining with OR gate. Here these are OR gates. Plus indicates or represents OR gate. So the given equation will be like this, and we have to understand this as in the form of gates. Now let us try to design a circuit for the given equation, for the given Boolean function. Now accordingly, here A and B, as I told you just now, it is a AND gate. How do you write AND gate here? AND gate we are writing like this. This is AND gate with one output and 2 input signal. And here one, this is A and this is B. And output of this would be A dot B, or A and B. Now look at one more circuit. This is one more gate, that is AND gate with 2 inputs. So here I am going to write one more AND gate, and here with output, and here 2 inputs, and here one input is A and another input is C naught, nothing but inverter gate. So we represent like this here. So this is the input C, and we are writing one more NOT gate. So this represent here C naught. This is C naught, input of this gate. And next one is this is one more gate, AND gate with 3 inputs. So we are going to write here one more AND gate with 3 inputs, that is, this is B, A naught. We have to write how we have written for this here. This is A naught, A, and here this inverter gate. See, this represent A naught, and similarly C naught. This is C with inverter gate and this. So this is C naught. There are 3 inputs and gate B, A naught and C naught. So this is the one. Now the output of all these gate should go to input, and here this is OR gate. So how do we write OR gate here? This is how we represent OR gate with only one output. What would be the input for this gate? Here input would be output of all the 3. So here this would be the input of one input signal, this is second input signal, and this is third one. So this is circuit of this given function. Now here every stage we supposed to write the output, and here output will be B dot C naught and A naught. So final result or final output would be the same given expression or function, that is A B plus A C naught plus B A naught and C naught. So this is how we construct this is how we can design a circuit for the given function. So this is a derived gate, and this gate or this circuit is designed with the basic gates. Now in the next slide you can see the same diagram. This is how we write or we design a circuit for the given function. Now let us write one more circuit for the given function or the equation. Again, if you look at this example, here x, y, z, there are three input signals for the function. This is x plus y, and you know that this plus stands for it is OR gate, and this is OR gate. Here one more OR gate, and this is one more OR gate. And here and after this there are three gates, and output of these three gates will be the input of this. There are two here. This is AND gate. This is AND gate. So in the previous example, it is A and B here. Now look at this. In this slide, it is A x plus y or A plus B. So plus stands for OR gate. So this is OR gate. OR gate, OR gate, there are three OR gates, and output of all the three OR gates goes to AND gate as input. Now let us draw the circuit diagram for the same. This is x plus y, this is OR gate. This is how we write OR gate, two input, this is one output, this is x and y. And here this is one more OR gate, one output, input x, z, and it is y plus z. It is one more OR gate, input y and z. So output of this gate will be x plus y, x plus z, it is y plus z. Now output of all these should go to AND gate. This is AND gate with one output, and input would be output of these three gates. And we represent the output here with the same given equation or the function. This is x plus y and x plus z and y plus z. This is how we design a circuit by using the basic gates. Now let us move on to next concept, that is universal gate. Till now we have learned what are different types of gates and how to design a circuit for the given equation. Now next concept is universal gate. See, universal gate is a gate using which all the basic can be designed. NAND and NOR gates are called as universal gate. Here, universal gate is the one. Using universal gate, we can derive or we can design the basic gates. Basic gates are AND or NOT. So, what are universal gates? From the universal gates, we can derive or we can design the basic gates, AND or NOT. That is the definition of universal gate. And what are all the universal gates? NAND gate and NOR gate is called as universal gates. NAND and NOR gates are popular gates, are less expensive and easier to design. And the basic gates AND, OR and NOT can easily be implemented using NAND or NOR gates. That is why we call NAND and NOR gate as universal gate. Next, we move on to next slide. And here, we are going to design. We are going to construct the basic gate. First one is NOT gate or NOT operation by using NAND gate. How do we draw this? But we know what is a NAND gate. So this is in the NAND gate, we know that this is how we represent NAND gate. It is AND gate followed by NOT. This is your NAND gate. And non-NAND gate will be having more than one input. So suppose this is X and this is Y. It will be X and Y bar or X and Y NOT. So this would be the result of this. But here, if we talk about NOT operation, now I want to convert this circuit into NOT gate or NOT operation. But what if you look at the NOT gate will be having only one output. If you look at this NOT gate, this is the NOT gate circuit or inverter gate. This NOT gate has only one input and only one output. This is what you have learned in our previous slides. So, how do we convert it now? See here, this NAND gate will be having two inputs, two or more inputs. So, how do we convert into one input? So, normally what we do is, we are going to join these two input and make it as one input. So, generally we say we have to short these two input or these two signals so that we will get only one output. That's what we have done here. In the diagram, you can see that here NAND gate and here these two inputs are joined together. We say you have to short these two input signals to make one input signal. So, if you look at one input signal, output signal is X naught as per the definition of NAND gate. How do we say this is the diagram and how do we prove this algebraically? So, this is, if we say NOT X will be the output of this. NOT X or X naught will be the output of this. If we say X naught, what is the input? X, this is NAND gate and it is X. X, NAND gate, X. And how do we represent this? This is how we represent X and X naught because it has only one input. So, X into X and this is not X into X, it becomes not X plus not Y by using the Boolean theorems. And again not X plus not, that is equal to X as per the Boolean equations or Boolean theorems. So, this is how do we construct the NOT gate or NOT operations with the help of NAND gate. That is the meaning of NAND to NOT logic. Okay, students. Now, let us look into another operation, that is OR operation or OR gate. Means how do we construct OR gate by using NAND gate or with the help of NAND gate. Now, this is, you know what is OR gate or OR operation. This is your OR gate with two inputs. Suppose this is X and this is Y, it would be X plus Y. So, but what is NAND gate? If you look at the NAND gate diagram here, this is NAND gate, this is, suppose here X and Y are the input, this should be X and Y not. So this would be your NAND gate. So here what would be the result of this? Now this is OR gate. So with the help of this AND gate, we have to construct or we have to design a circuit for this operation or OR gate. Now this OR gate will be having two inputs X and Y. Now look at this NAND gate here. This NAND gate will have two inputs, and as what you have done in the previous example, what you have seen in the previous example, we have to join these two input signals and make it as one input. So this is your X is one input. Similarly, one more NAND gate with two input, we have to short it, so it is one input Y. So this input is 1 X, it becomes X naught here because of NAND gate, only one input. So this is Y and it is Y naught. And if you look at this here, last this is NAND gate, here a small bubble will be here. So this is your one more NAND gate, and output of this will be X, and because of this, this is plus Y, X plus Y, and here because of NAND gate here, this will be removed, not will be removed. So this will be X plus Y. So this is the output what we expect from the OR gate with the help of X and Y are the two inputs. So this is how we derive OR gate or operation using NAND gate. By using different Boolean theorems, it is possible to prove the given circuit or OR gate by using NAND gate. Now let us look into one more operation, that is AND operation. What is AND operation? It is same concept. We are designing an AND gate by using NAND gate. Now this is AND gate, this is your AND gate, and this AND gate, suppose this is X and Y, this is X and Y. But what would be the NAND gate? NAND gate, AND gate followed by NOT. So suppose this are the two input X and Y, this is X and Y NOT. So now with the help of this NAND gate, we have to design a circuit so that output would be equivalent to basic NAND gate. Now look at the diagram here, or circuit diagram, AND operations. This is NAND gate, X and Y are the inputs, this is output here. And if you have one more NAND gate here, this NAND gate will be having two inputs here, but this is only output. So we have to short these two inputs to get the output of this will be the input of this NAND gate. So finally, result of NAND gate will be X and Y, X dot Y. So X dot Y, this is the output of AND gate. We have got this output here by using NAND gate or by using NAND logic. So this is how we design a circuit for AND operation. And same thing, similarly, we can be proved by using different various Boolean theorems. Next concept is how to design a circuit by using only NAND gate or NAND gate only. Now at the beginning, we have learned to design a circuit by using basic gates AND or NOT. Please remember that we have learned to design a circuit by using different basic gates AND or NOT. Now this concept is we have to design a circuit for the given equation with the help of NAND gate only or with the help of only NAND gate. Now what is the procedure for this? Here first is we have to derive simplified sum of product expression. This is the given expression, and first step is to draw a circuit diagram using basic gates. This is what we have learned in previous slides. Next, in this circuit, we have to replace all the gates with NAND gates only. That is how to derive a new circuit by using NAND gate only. Now let us see the example for this. Here, Now let us draw circuit diagram for the given equation. Here A, B naught C, as I told you already, A and B and C. This is your AND gate. This is AND gate, and this is one more AND gate, and there are two AND gates, and output of these two AND gate will be the input for this OR gate. This is the step number 2. So we have to draw the circuit, basic circuit, by using basic logic gates. Now let us try to draw the circuit diagram here. First A, B naught C, AND gate. See, this is AND gate. This is AND gate with 3 inputs. This is A, B naught, C. How do we write B naught? This is how we write B naught, with NOT gate. And one more AND gate with output will be here, and there are 2 inputs. One is C and B. Now this is OR gate, so we have to write the OR gate here, and this will be the output, and for this output of these 2 gate will be the input for this OR gate. Now here this is A, B naught, C, this is C naught, B. Now output will be A, B naught, C plus C naught, B. This is the second step to derive a circuit by using NAND gate only. The second step says, first we have to draw the basic circuit or the design circuit by using basic gates. So step number 3, the next step is have to replace all the gates with NAND gate only. So next step will be have to replace all the gates. So in this example, this AND gate should be replaced with NAND gate. So the final circuit would be like this. This is one NAND gate to replace this, and this is another NAND gate to replace second, and here we will have one more NAND gate to replace third gate. So here output of this will be input of this gate, and here this is A, B naught, C. So here one input is A, this is B naught, again here is B, this again also will be replaced with NAND gate. Here look at the circuit here, this is we are using inverter gate here, this one also has to be replaced with NAND gate. So here NAND gate with one input. Now one more input, that is C here, so this is C. Now for second one, C naught, B here. So this is NAND gate, this is C naught, and here B. Now output will be same, A, B naught, C here, C naught, B. The final output would be A, B naught, C plus C naught, B. So this is how to derive a circuit by using NAND gate only. First we have to give an equation, we have to draw the circuit diagram by using basic gates, then we have to replace all the basic gates with NAND gate. So this is how to derive circuit by using NAND gate only. The next concept is NOR to NOR logic, or how do we derive the basic gates, AND gate, OR gate, NOT gate by using NOR gate. In previous slides, we have learned to draw circuits by using NAND gate. Now we have to design a circuit or operations, basic operations of basic gates by using NOR gate. This is OR gate followed by NOT. This is your OR gate. So this is, suppose this is X and Y. This is X plus Y bar. This is your NOR gate. So with the help of this, we have to design a NOT gate. What is a NOT gate? NOT gate, it takes only one input and only output. Suppose this input is X, output would be X naught. So now we have to convert this circuit into this circuit. Now look at this. Here if you look into this NOR gate you will be having two or more inputs. So how do we make it to one input? So we are going to short these two input signals and make it as one input here. So it is one input and here is one output. For example, here this is input X and output would be X naught. So here X naught will be the output of NOT gate, but this is NOR gate. So by using NOR gate, we have derived a NOT gate or NOR operation. See, this is NOT X is the output of this, X NOR X, X plus X and X dot X. All these can be proved, can be learned by using Boolean theorems. Now, this is how the diagram. First, this is NOR gate and this is what I have written here with one input. Here we have to short these two inputs to get one input signal. So this would be the output of this. So this is what we get. Now let us move on to next operation, that is OR operation. Now this is OR operation, means we have to design a OR gate or OR circuit with the help of NOR gate. So you know what is the result of OR operation. Suppose this is your OR gate. This is A, B, A plus B. So this is your OR gate. So what would be the result of NOR gate? NOR gate will be OR gate followed by NOT, and this is, suppose this is, these two are the input and here A plus B naught. So this would be the result of NOR gate. So now next one is, now we have to convert this OR gate into OR gate. Now we have to convert this NOR gate into OR gate, that is NOR to OR operation. So now look at the diagram here, circuit diagram here. This is NOR gate with two inputs A and B, and this is the output of NOR gate as what you have written here. Now this NOT gate, we have, this is a NOT gate and we have to get the result as 1 here. So this is one more NOR gate, it has two inputs and we have to short it, and output of this will be the input of this one more NOR gate. So we will get the result A plus B. So this result A plus B is similar to the output of OR gate, that is A plus B. See, this is the circuit for NOR to OR operation. Now let us move on to one more operation, that is NOR to AND operation. Means we have to convert the given NOR gate, or now we have to design a circuit of AND gate by using NOR gate. Now this is, you know what is NOR gate? This is, suppose these two are this is A, B, A plus B naught. So this is your OR gate. And what would be the result of AND gate? If you look at the AND gate, this is AND gate and here suppose this is A and B are the input, output will be A and B. So now with the help of NOR gate we have to get the result of AND gate, that is A and B. Now look at the circuit here. So because in this example, there are two inputs here. Output is consists of, there are two inputs here. So this gate will be having two separate inputs. Now look at the circuit here. This is again NOR gate with only one input here, A. Here generally NOR gate will be having two or more inputs, but here we have combined these two terminals or two inputs to make one input here. So this is A is one input, B is one input, and output of these gates will be A naught, and for this it is B naught. So then output of these two gates will be the input of this one more NOR gate. So we get the result A dot B, or A and B. So A and B is the output of this NAND gate. So this is how we can design a circuit or a basic circuit and gate with the help of NOR gate. Next concept is to design a circuit by using NOR gate only. So in our previous slides, we have learned how to design a circuit by using only NAND gate. Similarly, now let us see what is the procedure to design a circuit by using NOR gate only. Now the step number 1, it is derive a simplified product of some forms of the expression, means this is the given expression. Next, draw a circuit diagram using NOT or AND gates. So same thing what we have done it in NAND to NAND logic. So we have to draw a circuit by using basic gates. Next, step number 3, finally we have to substitute NOR gates for NOT or AND gates. So we have to replace finally all basic gates with NOR gate. This is the procedure to design a circuit by using only NOR gate. Now look at the example here. Now let us design the circuit for NOR to NOR logic or NOR gate only. Now look at the equation here, x plus y. If you look at the expression, this is your plus stands for OR gate, and here is A dot. So this dot represents AND gate, and again this is one more OR gate, another OR gate with NAND gate. So let us draw the circuit diagram by using basic gates. So the x plus y, it is OR gate, this is OR gate, one gate, and here two inputs x and y. This is x plus y, and again y plus z, it is one more OR gate. This is one more OR gate with y plus z. Y and z are the inputs, and one more OR gate. This is one more OR gate. Inputs are z and x, z plus x. Now this is in between we have got AND gates, so we have to write here AND gate, and for this input would be output of these OR gates. This is how we write the circuit, and these three are the inputs and this is the output. So the final expression will be the output for this one. This is the circuit by using basic gates. Now in step number 3 or in a 5 step is we have to replace all these gates with NOR gate. Now let us try here. So this is 1, 2, 3, 4. Here we have to write all NOR gate. This is OR gate followed by NOT. This is one gate, second gate, and this is third gate, and here inputs x, y, y, z, and here z and x. Again, this gate also has to be replaced with NOR gate. So this is one more NOR gate, and here so here output of this x plus y naught, this is y plus z naught, and here z plus x naught, and here final result will be the given expression x plus y, y plus z, and z plus x. So this is how we design a circuit by using NOR gate only. Thank you very much.